Después, si quieres.
No.
¿No hay problema? Bien. Te voy a pedir que
Caraca, dois que nem eu.
Sim. Gabriela. Gabriela.
Pelo menos a gente tem sobrando, se tivesse uma coisa.
te voy a pedir que estés entre aquí.
Ya.
Por caso de encuadramiento.
Sí, ¿dónde me paro? ¿Aquí?
En el máximo. Puedes caminar por aquí. No, espero que está bien. Ven. Sí, creo que es. Sí, estoy.
Sí, está.
Aquí.
A ver, ¿dónde queda ahí? Ya. Sí, pero este lo graba o lo transfiero.
Lo grabo, si quieres, después puede venir.
Just I want to say something stupid.
Okay, you can see this later. If you it's okay, we share.
No, that's it. I will not just mention this
No,
much time.
I didn't write for please withdraw and then withdraw this.
Hello, people. Hello.
More than 7.
Yeah, more than 7.
Isso ainda assim uma expressão mesmo. Verdade, expressão. Para você ver essa específica também. A rede aprimorada, isso é livre. Inside the university. Building inside the university. But here, just some and postgraduate students. Students that are taking the master degree, the PhD, some of them live around, some of them are very far, some of them are out from the normal times, during the period of lectures or classes, and I have to schedule another because the center is 200 and 300 persons.
Sometimes when we ask for talks or we have 4, 3 people. So that's why it's 5
I don't know if Guilherme will take pictures. But my camera is really bad, not so good. It's very poor. Anyway, welcome everybody. Here we have a pleasure to guest Professor Victor today from his university.
It's a long name.
But Professor Victor took his master degree under the supervisor Professor Miguel Zaghi, Professor Miguel Zag is very well known from us on quantum optics. He has a great book on quantum optics. I guess everyone who's doing quantum optics knows Professor Miguel Zag. And then Professor Victor moved to London to his PhD under the supervision of Professor Sugato Bose. Sugato Bose also is a well-known name in physics. Today he is working with, Professor Sugato is working with Montenegro, and Professor Victor starts to move to another area, for example, quantum metrology, which is our collaboration. Professor Victor has collaboration with people all around the world, including here in Brazil, Uberlândia, and of course Chile. He did his graduation in Universidad Católica de Chile, and then he started to do research. Nowadays he has approximately 24 papers in this area, and he is a very young researcher. It is open to collaboration, so if you want to collaborate with Professor Victor, just go to my room and we start collaboration. Okay? It's my pleasure to present Professor Victor that we will think about sequential measurement quantum metrology. Professor Victor, what is your university? Sorry to accompany you, but
Okay.
your university is?
It's Electronic Science and Technology of China.
Two postdocs, one in Chile and one in China.
And same universities.
Same university. Now he is a position, permanent position in this university. Okay. Thank you very much.
Thank you. Well, thank you, Professor Rotter, for this kind introduction. First of all, I would like to say that this is my first time in this city. I visited Brazil many times. And, before I start my presentation, I just want to show you a little bit of my city, where I live. So I live in China, as Professor Martin said. I live in the province of Sichuan. It's about 80 million population. And the city where I live is called Chengdu. It's about 20 million inhabitants. And it looks something like this. You can take the same picture from a beautiful bar in a rooftop in a building nearby. This area is the party place, which, as far as I know, is kind of translated as the drunk area for foreigners. That's the translation. And this is a very famous bridge in the city. It's where Marco Polo walked through the Silk Road. It's in Dockman Bridge. And it's a beautiful city which kind of contrasts between the traditional Chinese and the modern city. For example, you can see this is how it looks like, more or less. You have plenty of parks like that with really tall buildings around. This is the latest museum that we have in the city. It's the Science Fiction Museum, where the Hugo Awards were given last year. And of course, Chengdu is very well known because of the panda. It's the panda city. It's where the pandas live. We have different panda bases to do research on them. And this one you can pay to hug them and visit them and see these little panda babies in September. And these other ones are called the red pandas. They're smaller, but they're free, so they can just walk around your feet. And around Chengdu also you can find, for example, this beautiful mountain is called Mount Jincheng. And it's very famous because this movie was based on that area. And also you can find, for example, this area, which is the irrigation system. It's a dam. It's called Duyanyang. It's many, I don't know how many years ago, they built this dam to take advantage of the river. It's a beautiful place too. And also you can see the Mount Emei. We take all our visitors there. You can see this one, which is really beautiful. You have to go early morning at the summit of the mountain, which looks something like this. And you're above the clouds, so you can see this ocean of clouds. At least how they set it like this. And finally, I just want to show you this area for people that they love hiking. This is the Mount Sigunian, something there is composed of four mountains. Sorry, this I think is about 6,000 meters above sea level, and you can also do this hiking if you're adventurous enough. So this is more or less about where I live. And now let's start with a little bit of physics because I have a limited amount of time. As Professor Norton mentioned, I'm going to talk about sequential measurements quantum metrology. Quantum metrology is a very famous now area of research in quantum technology, together with quantum computing, quantum simulation, quantum cryptography, and so on and so forth. But in this title, I just want to emphasize that this is a sequential measurement strategy. It's a non-conventional way of doing quantum metrology, and it's based on a latest paper that we published, I think, last year or 2 years ago. So let me start with a little motivation about estimation. I put it like beyond estimation because I want to present two main perspectives of quantum metrology. The first one is the most classic one, that in physics, of course, as we know, we're all physicists here, measurements are very important. Experimental physics, they know this for sure, right? We need to measure stuff to progress in science. So, but many of these quantities are not really accessible directly. You can think, for example, there is no observable for coupling constants, or entropy, or entanglement, and so on and so forth. So how can we estimate them? Actually, we don't measure stuff, we just estimate them. So I thought, as an example, for example, I asked this question to my 10-year-old nephew the other day. So how do we measure the mass of the Earth, right? It's a quantity that we, in principle, we cannot measure directly. So one way I thought, okay, we can use this formula, the density of objects, right, as a ratio between the mass in a volume, right? So I put these two guys here, Eratosthenes and Archimedes. So as you know the story, Eratosthenes, about 2,000 years ago, he measured, well, first of all, he realized that the Earth is a sphere, and he measured more or less the radius just by geometrical aspects, and he got this number, which is very, very close to the real value. Real, I will explain what real means later. And then we need the density. So the density of what, right? So you can go outside and have a look what you have around. And I checked this on Wikipedia, like what is the most common stuff outside. You can see the trees, the water, whatever. But you can see that the density using granite and basalt, which are the stuff, the most common stuff rocks outside. And then you put these things, you do the numbers, and you get that the mass is more or less of the 10 to the 21 kilograms. That's the order of magnitude. So the question is, how do we know that this is the value, right? So then you think a little bit, you take your first course in physics, and you realize that there is another quantity. It comes from this guy, right, Isaac Newton. I put these other guys because I give this talk in Italy, so I put totally Italian guys. And so you know that there is a model in physics that there is an m going around. This m is the mass of the Earth. So you have a model in which you can encode this parameter in a real field. So now you can put r as the radius that Eratosthenes found, g the constant that it was measured in the 19th century, and you do the math, and then you get another value, 10 to the 23. Okay? So it's 2,000 years apart, and there is 2 orders of magnitude difference. 2 orders of magnitude is a lot, right? But we are talking about some very simple estimation, and this one with a full physical theory. Great. So now, how can you estimate the mass of the Earth in another way? You can think about. And I put Einstein before for other purposes, is because you can also measure the mass of the Earth by encoding the angle of which light deflects, right? And using the theory of Isaac Newton, you cannot really tell. There is no angle. The space curve is flat, and there is nothing deformations. So the other way of looking at metrology is that you can test theories too. If the parameter is there, how it's predicted by the theory, and so on and so forth. So you can find many examples in this way. For example, the uncertainty principle. I don't know if you are aware of, but there is some corrections of this quantity if you consider gravity effects and so on. You can find the Andrew radiation if the temperature can be estimated. Hawking radiation also hasn't been detected, so you can amplify the signal to estimate these parameters. You can check the discreteness of time in Carlo Rovelli's ideas. And for example, this one, which I like very much, I'm not an expert in the area, but if you want to estimate the vacuum energy density of the universe, then if we put all the Feynman diagrams and all the theories that we have, everything very precise, there is more or less 100 orders of magnitude off between theory and experiments. So we can really think of how can we use quantum metrology to really test the theories in this aspect. Okay, these are the two ideas. Then you can use quantum metrology to really estimate small parameters, very weak signals. And the other one is like to test theories. The standard sensing procedure is divided into 4 steps. Okay, the first one is you have a probe, like for example a thermometer, which encodes something, in this case the temperature, and then you have to perform measurements on your physical system, and with the measurement system, with the measurement outcomes, you have to estimate the value with what you have from the experiment, right? For example, we want to estimate the speed of light, okay? So you can use a chocolate as a probe, then you can put it inside a microwave, and you put 1 minute in the microwave, and the chocolate bar will be melted into some spots. So because you know that the microwave is a resonator, the antinode is going to be the one with the maximum intensity. So you can say that there is a wave, you have everything, the wavelength. You turn around your microwave and you see the frequency at which works your microwave. And then you have the relationship between the speed of light. So the measurement in this way is just with a ruler, you just measure the distance between these two spots, and then you do the math, you do the estimation in your notebook. And these people, you should check this video from Nottingham University. I think it's number 5 or something like this on YouTube. And these people estimate the speed of light with a chocolate bar with 30% uncertainty. But the question is, again, how can we be sure of if this is the real value, right? Okay, so extracting information is very difficult. We know that, for example, if you want to look at a particle, you have to shine some light and then detect the light the other way. So there are many ways you can really shine light with low energy, 1 photon at a time, or strong measurements, and so on. So there are many works in the literature of how to really extract information from a system. You have the weak value measurements, the weak measurements, the strong measurements, projective measurements, generalized measurements, etc., etc. See, there's another slide here. Okay, for example, this one. This is quantum metrology with imperfect measurements. There is this one was very famous from the Brazil team, where you have a general framework of how to recover the estimation bounds if you look at the photon losses. All right. So, okay, this one also is important. There is another approach in which you can continuously monitoring your system to achieve better precision. Okay, so 2 questions that I want to present now. So the first one, I have been repeating myself a little bit, is how can we be sure that the estimated unknown value, the value is always unknown, right, is adequately estimated? And the second question is there a limit? Is there a limit to the estimation of a value? Okay. So let's have a look at these two questions. To answer these things, long time ago, there's been addressed this question using what is called parameter estimation. Okay. So in general, these things you can see from calculus. It's a direct application from calculus, which is called the error propagation formula. It is typically used in experiments. Some ways there are some promising theories. So it's really not an operational way of estimating quantities. How can we do this much better? I have these slides in general if you consider d unknown parameters in your system, but usually let's focus in that's only one. So imagine that you have theta. Theta is your unknown parameters that you want to estimate. Okay, one good figure of merit is defining this quantity. Okay, this is the uncertainty. This theta with this upside down hat is called estimator. And this is the true actual value. Okay, that's the difference. The problem is like this value is always unknown, so it's not very good figure of merit. It looks very good from a theoretical perspective, but actually you never have access to this value. Okay, so there are many people thinking about this question. So what do you actually really have in experiment? So what you really have is that imagine that you have one parameter to estimate, theta 1, and then you perform different measurements in your system, and you get a set of measurements outcomes x1, from x1 to xm, for example. You have all these values. Okay? So what you're going to do is that you're going to take all your values, and you're going to put it in it's called estimator, and the estimator is going to give you the value. So it will jump to the set of parameters into the estimated values. This part is always classical. Okay? There is nothing quantum here. I haven't even said the word quantum. Everything is classical here. So the estimator is always classical. For example, you can just imagine that you're tossing a coin. You want to know the fairness of a coin. So how do you estimate the fairness of a coin? You just toss it. 1 time, twice, 3 times, 4 times, etc. And then you say like, how many heads I have, how many tails I have. That's your estimator. If you want to do something more fancy, then you can use machine learning, reinforcement learning, and all these machine learning things that you can think of. But this step is always classical. Okay, so a much better figure of merit is this one. This one here. So this is your estimation, and this is the expected value of your estimated depending on your set of measurements. So this figure of merit, this one here, only deals with your measurement data. There is no actual value, there is no true value. Okay? So you can define it like this. This is the expected value, right, over your probability distributions. And then you end up with something like this, where this B, where this B is the bias of your estimation. Usually we work with unbiased estimators, so it means like in the long run, when you make many measurements, this value, the estimated value is going to be your actual value, and this is going to be 0. This is called unbiased. So basically, what we work is with the covariance matrix, or in our case, for one unknown parameter, just the variance. This is the theory of Lecan's theorem. I can give you the reference later. Okay, so let's look at this from a little bit mathematical perspective. Very simple. So any positive semi-definite matrix product can be defined like this, where x and y are these quantities. I will just skip this part quickly. So this is important. So I just replace the x and y that I defined it over there, here, and doing some little math, just doing the multiplication between these values, you get this expression. So the most important is T and G, these quantities, and you can prove that the covariance matrix of your estimated value is larger or equal than this expression. T G minus 1 T transpose. Okay. It's not that important, that part, because it's going to be summarized in a very well-known quantity. Okay. Here. Let's see a particular case. You can consider any function G for fulfilling the inequalities that I showed in the previous slide. But let's consider this one. This is a score function. It's known in statistical analysis. Also, it's very good, for example, if you think of tossing a coin. It's really good for regularity conditions. It's smooth. It fulfills, because of the logarithmic here, is additive with conditional probabilities, etc. So it's a good function. Let's keep it like it's a good function. It's a good representation of what we want to estimate. So if you replace this one, it's very easy. You can just plug these things and do the integrals and everything. Then you realize that T is 1, very simple, and G is this quantity, which we will call it I. And this I is called the Fisher information. I will put this adjective here, or noun, I don't know, classical Fisher information, because when the Fisher information was discovered, there was no quantum part, so we call it Fisher information or classical Fisher information. So, what does it really mean? What does it really mean? You're in the lab, okay? You're in the lab and you want to estimate a parameter, unknown parameter theta, okay? If you fix your measurement basis, you will get a probability distribution associated with that measurement, with that specific measurement. What this quantity tells you is that the uncertainty in that unknown parameter cannot be lower than this quantity. It's bounded. Yeah? That's the classical, this is what we call classical Fisher information. So, okay, so have a look at this one. This quantity only depends on the conditional probability and the measurement outcomes, this X. Right? So, let's go back to our original questions. The first question is like, how can we be sure? Well, there is a whole parameter estimation theory framework, okay, that tells you exactly what is the bound. So, is there a limit of the estimation of value? The answer is yes. You can use the Cranach-Rao inequality, which is this one, which tells you like you cannot do lower with that specific measurement basis, right? So the obvious question is like, can we do better? Maybe changing the measurement basis. If you have this measurement basis, you get this uncertainty. If you change the basis, then you get another uncertainty. Is there a maximum? So the answer is, well, I'm not tell you the answer, but I can tell you one concept. This I will paraphrase Professor Mateo Harris, who said that in that in classical physics, probability is not extremely well defined. It's just what you measure from a random variable, and you get results in return. But in quantum mechanics, the probability is very well defined operationally. The probability, we just use the Bond rule. For us, in quantum mechanics, the probability of a certain outcome is the trace of your P of m times your state. Right? This one. Without the derivative here. The probability is just the trace of your P of m with your state, encoding your parameter. So now we have an operational way of seeing the probability. What you do now is, let me see if I have it here. You look, have a look here. We need the probability. Okay. So now we have the Bond rule. We're going to plug it here, right? And we need the derivative of the probability. That's why I put the derivative of the probability. The derivative here and the trace, you can swap it, right? Under certain conditions. under certain regularity conditions and the smoothness of the curve, etc. If that is the case, and you can swap it, then what you actually want is the derivative of your state. And the derivative of your state, it satisfies this equation. It's an implicit equation, a parametric equation, which you introduce what is called the symmetric logarithmic derivatives, SLDs. These L operators is a sub-adjoint operator. This is the anti-commutator. So you have to solve this equation to find the derivative of your operator. But the cool part is that when you plug these things in the probability and you do the integral, you can use the Cauchy-Schwarz inequality, etc., etc. You can optimize over all possible measurements, over all possible classic measurements in using the Born rule in quantum mechanics. So you will end up that the classical Fisher information is actually upper bounded by this other quantity that we call it quantum Fisher information, which is now what you have to do is you have to take the trace of your state multiplied by this operator n that you have to find. Okay? So now there is another inequality. It's called quantum Kramer bound. Okay? In 2 slides ago we have that. This is theta or unknown parameters. Okay? The variance of your unknown parameter is larger than the classical Fisher information, and this one is larger than this other quantity that the quantum Kramer or quantum Fisher information. Okay? So this is the ultimate precision limit. You cannot do better than this. This is the lower bound. There are different ways that you can compute this quantity, the quantum Fisher information. For example, this one is one expression. It's not terribly important. This is the quantity that, for example, we use typically. It's called the quantum Fisher information. It goes something like this. It's not very difficult to evaluate it. And for pure states, adopts this very simple form. I didn't mention this, but this is a metric. It's called the Fubini-Studi metric for quantum states, pure states, for vector states. And this one is related to the Mures metric, which is the distance for density operators. So there is also a geometric aspect of classical and quantum Fisher information just for measuring parameters. This is not very important. And okay, that was for the single parameter case, i.e., just I want to measure one parameter, a known parameter. But this is not typically the case. We have many parameters that we want to estimate, and for this case, everything gets really complicated. Okay, I have just one slide because also I haven't worked heavily on multi-parameter estimation. But now we have the covariance matrix, and we have inequalities between matrices. This is a bit toxic. It's a bit ill-defined somehow, right? So what people usually do is the generalizations of the quantum Fisher information, the classical Fisher information. What people usually do is that you move from the matrix inequality to a scalar inequality, and to do this you just put the trace of a weight matrix, okay, over here, and depending on your W that you pick, then you get different bounds. So it's a bit complicated, this part. And you can think now, for example, if you have two parameters that you want to estimate, and you have one measurement, the question is the question about what is the optimal measurement to estimate both parameters is a bit also ill-defined, because now you have two. So which one you optimize, right? So this is because there is an incompatibility nature of between parameters, which is defined by this one, is because the SLDs that I defined before, they don't compute. So now you can think of either I want to optimize the measurement for parameter 1 or parameter 2, or maybe both at the same time, but having a trade-off of others, etc. But for us, we're going just to work in single parameter estimation for the time being. So now, we have a beautiful operational meaning of estimating parameters. Let's go back to our experimentalist here. So the experimentalist wants to estimate a parameter, a known parameter. Most likely, he will work or she will work in this region. Because not every measurement is available in the lab. So in the lab, if you pick your measurement and you get probability distributions, then most likely you will be in this uncertainty. Okay? What we can tell him is like, you can do better if you do this measurement, or if you do this quantum control, or if you do this, for example, if you use another resources of quantum entanglement and so on. So you can do much better to estimate your parameters. Okay. So this is the operational meaning. One key point here is that the quantum fission information doesn't tell you which measurement you have to perform. It's an optimization protocol. The quantum fission information, for example, here, I can tell you that this quantity is 100. Who knows? Any value. But doesn't tell you explicitly which measurement you have to perform. There is a way in which I can tell you. It comes naturally from the SLDs, the L sub-adjoint operators that you can compute. But usually these L's are very complex to do in the lab. That's why we still, the theoreticians, we want to tell you how far are you from this bound. Maybe with your simple measurement in the lab, you are not that far from this value. So it's a trade-off. Okay, let's go back to our question time. So can we do better? Yes, we can. We can go up to here, but no better. This is the ultimate bound. You cannot do better than this. Okay. So the question is, so what? Okay, we just get this one. So this is the quantum metrology aspects that I want to mention quickly. So you have the quantum advantage as an example. Imagine that you have this state. This state is a separable state. You have 0, for example, plus 1. This plus state repeated n times, disentangled from each other, n particles, and you have this kind of family of states with local Hamiltonians hi, and the parameter that you want to estimate is outside your local Hamiltonian. Okay, this could be an integer parameter, for example, and then you can prove that the estimation, the uncertainty in measuring this theta, goes something like the square root of nm. N is the numbers of particles, and m is the numbers of repetitions of your building statistics. Okay. So, if you do exactly the same numbers of particles, you have n particles now, but you have a GSZ state, right? So all of 0, 0, 0, 0, 0 plus 1, 1, 1, 1, 1, 1, highly entangled state with the same Hamiltonian. Okay, you want to estimate the same parameter. Now your estimation is n. You get a square root of n advantage. Okay, this is the core of quantum metrology. With the same numbers of resources, you can get better estimation. Okay. Well, this is a very restricted Hamiltonian. You can think, for example, in another Hamiltonian. This is the Ising Hamiltonian. You can see, for example, here you can compute the quantum fission information, and here's the ratio between the magnetic field here and the exchange interaction. You can see that there is a huge peak here, massive peak, minus 1 and 1, which is the critical point when you jump between ferromagnetic to paramagnetic phases, because the properties of the states changes abruptly, right, from one side to another. So people have used quantum criticality for quantum metrology for a long time now. There are general bounds, etc. There is a problem, this one. You can see that this is very, very highly peaked, right? And so if you move a little bit, just a little bit of your quantum fission information, everything goes linear with the numbers of particles. If you are exactly at the point, at the peak, then the quantum field information grows quadratically. It's called the Heisenberg limit. Otherwise, it grows like a short noise limit. Okay. Okay. So yes, this is the last slide of question on time. So what? This is the most important again. For the same numbers of resources, you can get much better sensitivity. Okay. So sorry, how long I have? Maybe 10 more minutes.
Don't worry.
So all good? All good so far? So far so good? Okay. So drawbacks until now. I try to sell you this quantum metrology for people that are working this, but there are many drawbacks of this one. Okay. So I put 9 drawbacks so far. First one is that even though I can tell you the quantum field information is, I don't know, 1 million, it's very high quantum field information, and the problem is like the optimal measurement is a highly entangled measurement that is impossible to make in the lab. This is one of the problems. Also, usually you have to have access to the whole system, also complicated. The GSE state that I show you, which has Heisenberg limit precision, if you lose one particle, then you are done. No more entanglement. The coherence is always a problem in quantum optics and everything, quantum mechanics basically. It's very difficult to prepare optimal entangled states. Like for example the GSE. What I put here? Oh, multi-parameter states is always complicated, as I told you, because of optimality between parameters. It's very local in the sense of if you move a little bit away from the critical point, then everything is destroyed. And we have to define the resources adequately. Okay? So, I want to focus to introduce a new way of estimating parameters in a non-conventional way, and we're going to relax this one, this one, this one, and this one. Okay? The first one is like I will show you that you can have any initial state. Doesn't matter. The protocol I show you doesn't depend on the initial state. You will access the system locally. There is no optimal measurement. You can pick, for example, a very feasible measurement in the lab, and the definition of resources is going to be defined in terms of time. Okay. So I will address these four questions. So I will try to relax this quantity actually in a better way. So the new concept is called sequential measurement scheme. So as I told you, when I give the example of tossing a coin, the fairness of a coin, I toss it once, twice, 3 times, 4 times. So there is an assumption here that I didn't say because I hide it on purpose. Is that every time that you toss a coin, the new measurement outcome is independent of the one before, right? We know this from this distance. So this is called IID, identically independent distributions. So, but there is a concept in quantum mechanics that we know very well. That there is for example, in strongly correlated systems, like when you have spin chains, for example, a local measurement produces a global wave function collapse. Therefore, if we want to measure sequentially, the sequences of measurements depends on the outcome before, right? So we want to use this aspect of quantum mechanics. Before this, usually conventional metrology uses quantum entanglement, right? Like the GSE state I showed you before. In this scheme, we don't want to use entanglement per se. We are going to build entanglement in time with the global wave function collapse. So this is more or less what we have. So imagine that you have a system and you have different subsystems. Right? You can think of, for example, James Cummings, for example, qubit and field, or you can think of a spin chain or Kondo model with different kind of impurities and different exchange couplings, etc. But this is very general. So we will have a subsystem. We will look locally construct system. So this is more or less what we're going to do. We're going to measure and free evolve the system, then measure again, and free evolution, and measure again, etc. So what we're going to have, something like this. This gamma 1 and gamma 2 are going to be quantum trajectories. So these are the times that we want to measure. Could be any time, but we just separate them regularly. So one trajectory you measure and you get 0, 1, 1, blah, 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 blah. Then at some time, because it's lunchtime, you stop and you make another trajectory later on. That is 1, 1, you get another sequences. Of course, the first one is with what is called a standard sensing scheme. You measure once, and then you restart your system, and you measure twice. And then you restart your system, and so on. But in the sequential measurement scheme, what you get is an m numbers of non-IID measurements. Okay? Because all these things depends on the conditional value before. This is the scheme. This is the main message of my presentation today. I'll give you one example. We will take this finite size trajectory. So we will have many particles. This is the first site. This is the site n with an exchange interaction of j. This is the Hamiltonian we consider. You can consider any Hamiltonian you want. We just consider this one. This is Ising chain in transverse and longitudinal fields. And we're interested in measuring this field that we don't know. This is an unknown field. So we call it magnetometry for obvious reasons. And the most important thing is like we are going to measure this guy. Only the yellow block, not the rest. So it's a local measurement. And it's not even where the field is, the unknown field is. But because all these things are strongly correlated, if you compute, for example, the magnetization between the first qubit and the n qubit, there is some sort of synchronization of how the spins, transfers the spin flip between neighbors. Right? So this is one way, a little bit of saying like this. You can use it as a remote sensor. Imagine that you have a very long chain, and you just measure one extreme. The other one is a non-invasive measurement. Okay. So in this particular case, for example, we start from the ferromagnetic case, all the spins down, the ground state of the system. Could be any state, right? But we want to show that, for example, this system has no entanglement whatsoever. And this is the ground state of the Heisenberg, the Ising chain in the absence of the magnetic field. So once the magnetic field is present, then you will evolve the system according to the Schrödinger equation. And then we were going to just measure in sigma z basis, a very simple measurement that you can do in the experiments. So what you're going to get, you're going to get either a spin up or a spin down. Spin up, spin down. It's like a quantum coin, right? And then you repeat. You measure, you keep that, you record the measurement, and then you evolve for some other time, and you keep the other measurement in your pocket. After that, you will have a string of zeros and ones. Now, the classical Fisher information is a little bit different because now you have to take the classical Fisher information of the whole trajectory. So, in our case, we measure 10 times. 10 times means 2 to the 10. So, it's a long trajectory space. You have 2 to the 10 trajectory space. It's like a binary tree, right? So this is important because we cannot do larger 2 to the 20 and so on. I forgot this word. Not approximate. The estimation comes something like this. This is not important. You can use just the variance, not truly relevant, this quantity. But, okay, so to prove that measuring sequentially really helps, we just compute the classical feature information. And it looks something like this. Okay? So this is the inverse of the feature information. Therefore, is the variance of your state. So the lower, the better. And therefore, this x-axis is the numbers of sequences that you perform. As you can see, we just presented two, but it's a general result. Whenever you're measuring more than once, it helps in the estimation. The uncertainty of your value drastically reduces. It goes really, really down. Okay? And it goes down, for example, you can fit a polynomial here. The fitting here has to be very carefully because it's only 12 sites, 12 measurements, sorry. But the polynomial goes superlinearly. For example, here is 1.5, 1.3, etc. It's always larger than 1. Okay. Yes.
You tell me that you have about 6 or 6 to 10 minutes to
Okay, no problem.
just to
It's lunchtime. Yes.
okay.
I understand. Yeah,
If you
yeah.
need more,
No, it's fine. It's okay. So, the one thing like I didn't mention, maybe slightly, is that both the classical and the quantum feature information are bounds. It's a number, right? But it's not an estimation. So how do you estimate? There are many ways. I mentioned, for example, machine learning and so on. But one that we use is the Bayesian. The Bayes rule is also very, very used in statistics. So it's just how do you update your knowledge about a quantity with new knowledge. Okay, so it looks something like this. So you have a prior beliefs. For example, more or less in this room are 25 degrees, I don't know, 25 degrees, that's my rough estimation. But maybe someone can tell me a little bit more information, which is going to be my evidence. Okay, I can perform a little bit more measurements. And then this formula can put all together and give you another belief. So it kind of update what you think with new evidence. Okay? So this is important. This is how it looks like. This is your posterior with the likeliness of your estimation. So if you want to estimate a parameter, unknown parameter of 0 point in the magnetic field, you see that as you increase the numbers of sequences, the likeliness of that value shrinks, so reduces the uncertainty and gets a larger peak. So what it tells you is like the uncertainty measuring that unknown parameter is better as you increase the numbers of sequences in this scheme. However, there is a trick here because I keep fixed the numbers of trajectories. Okay, so of course it's obvious that if you keep the same numbers of trajectories and you increase the numbers of sequential measurements, right? You have in reality more measurements. If you have more measurements, it's obvious that you're going to get better estimation, right? So how can we fix this? To fix this, we have to define our resource. And our resource is going to be time. Okay? You have 1 hour to run your experiment. Okay? So we put the interrogation time. This is very conventional interrogation time in experiments. It's something like this. So in strongly correlated systems, the initialization time is really time consuming. Cooling your system to all the ferromagnetic states is very time consuming. So every time that you restart your system, it's bad. Let's put it like this. So our protocol, what it does is like it uses the time more efficiently. This is what it does. So as you can see, well, if you do the proper fitting, etc., for a fixed time, for a fixed t, we can put all together and condense the estimation into this quantity. So the estimation scales as the total protocol time to the -1. This exponent nu is 1, which is the usual value that you can found. but also it's multiplied by the numbers of sequences to the beta, where beta is larger than 1. So this is a clear signal of quantum enhancement if you keep measuring in a non-IID way. So this is the main message of my talk. The rest I will give you something very simple. It also works for multi-parameter estimation. For example, here, and we can also do the same analysis for when you have more parameters to estimate. It's very robust. If you put, for example, the phasing in your spin channel, anisotropies in your exchange interaction, etc., you can also do all this kind of analysis, but it's very robust. And for long trajectories, when we can approximate it using Monte Carlo simulations, it also works. However, it shows something which is has been shown in the literature before, which is there is a saturation. So if you measure 5 times, you get quantum enhancement. If you measure 10 times, you get quantum enhancement. If you measure 1,000 times, then for the time 1001, you get really little information. You get saturated in your trajectory. How can we see this? We can consider this light matter model. I have 3 views to show you. So, for example, let's change the model, and we have James Cummings, and we're interested in measuring the qubit many times. So, as people from quantum optics they know very well, if you do the evolution, there is no measurement whatsoever. It looks something like this. If you measure and you don't record anything, you get the mixing. And if you measure every time and you keep the result, either you are collapsing the state with each measurement, the qubit measurement acts like a filter. So the Fock space basically picks at one, at some n value. And of course, you should expect something similar for the spin chain model that I showed you before. So you have this is the block sphere for this side view and the top view, and you have the first qubit, the middle qubit, and the end qubit where we measure. This is where the magnetic field is. So as you can see, as the time passes, when you measure, the first qubit gets in the middle, so it's the identity. The middle qubit also, and the end qubit is flipping, right, when you are measuring 0, 1, randomly, 0, 1, 1, etc. So if you look at this, the fundamental entropy looks something like that, right? So there is a region in which something magic happens, and then everything gets saturated, everything gets really mixed, and then no more information you can get from your problem. Okay, I'm almost done. This is basically what I just mentioned, that the saturation happens. This is to show that there is a work, this Daniel Ruger, 2015, that using some functionals, he proves that the classical fusion information in the asymptotic limit scales linear with the numbers of sequences. So the saturation is achieved. Okay, so this is the last part I want to say. This is a theoretical work. Okay, I talked with some experimentalists, at least in the strongly correlated systems, and they told me that they can maybe measure 4 times. Okay, so there is a long route to really prove this experimentally, but the quantum enhancement should work regardless of the system, regardless of your initial state, regardless of your measurement basis, etc. So it's a very, very general and systematic work. So there are many open questions. For example, you can pick the trajectory. The trajectories are randomly, but maybe there might be a way of quantum control these things. Well, there are several ideas that you can follow in this line of research. And in summary, just three main ideas that non-IID measurements, they are very good for sensing. Okay, this is non-conventional sensing. The second one is that we are using let's say, entanglement-induced dynamics. So we are not using entanglement per se, but instead we are using the wave function collapse as a resource. And it's a very general scheme. As I said, it works for any system, any Hamiltonian you want to have, it really works. So this is my university. This is the beautiful Jinko trees that you can see in October. And of course, we are hiring postdoctors in our group. If you're interested or you find these things relevant for you, you can text me or talk to Norton directly. So that's all for today. Thank you very much for your attention.
Good afternoon. We have a room for 2 or 3 questions. I have myself question, but I prefer to ask Professor Victor later in my room. Or then we can go to the blackboard and discuss more there. But I have general questions. So,
you can go back in the equation that relate the uncertainty, the delta n and n that has the square root of n, the size of stage.
you mean the Hilbert space dimension?
Yes.
Is it not this one?
Yes, yes. And these are the next.
The next one?
Probably I didn't understand well, but it looks like to me this equation says if you have a bigger dimension for your Hilbert spaces, it's saying that your number of measurements you need for a given fixed uncertainty, given fixed certainty, will be less.
Yes and no. So
Smaller.
it's not that the larger Hilbert space is some way, right? It's the numbers of particles. It's the numbers of particles. Yes, you're right. You can also think it as a Hilbert space.
But if you have more particles, you need less measurements. It's really difficult.
Okay. You need, if you have larger n, you need less m to achieve the same uncertainty. Yes. But usually we think the opposite. For a fixed m, you need, with the same numbers of particles, you get better uncertainty. The delta theta is smaller. Just a little comment on this. There is another resource for quantum metrology. It's called non-gaussianity. So, in the idea of that, you mentioned that Gaussianity, like for example, yes, coherent states or exclusive states are Gaussian. But if you let the system to explore a larger Hilbert space, like for example nonlinearities or other stuff, if you let your Hilbert space to spread the information, then also you get a better sensitivity. I didn't mention this thing because there is a proper way of line of research for spreading the information in Hilbert spaces.
This is the standard quantum limit. Yes.
This is the previous one.
This square.
Square root of n. Yes, it's the standard quantum limit.
So this is because you said that usually you think that not in terms of this n, but this m. Because sometimes this is going to inverse of just m, not the square root of m. And this is the maximum, we say, the ultimate limit. If this is not square root of m, it's a question. It's possible to have this with not the square root of m, but just on the
yes. Because again, I put it here. Most likely, this one is the standard deviation, right? The standard deviation goes like the square root of n. But in the I should change this one. In the original part of the talk, I mentioned always the variance.
Yes.
And the variance goes like if you consider the variance, this goes like n square m. Right? And they call n square as the Heisenberg limit. But this one is just to say that if you use a different probe with entanglement, then you get a gain in the numbers of particles. That's the main message.
Yep. It's okay? Other questions? No? We thank again Professor Livre for the nice talk. Thank you very much.
Thank you very much.
So much for your talk. And I hope you enjoy it. And let's thank again Professor Livre.
So I shared the talk with Professor Norton. So if you are interested, just ask him directly.
Yes. I have these slides. Somebody one? Just copy. Ok. Obrigado novamente. Graças. Lucas. Muito legal. Acho que eu não fiz como.